Welcome to this focused deep dive. Today we're really zeroing in on the core ideas of network architecture and security.
Yeah, exactly.
Think of this as like your streamlined guide through some really fundamental stuff. It's curated from the Google Cybersecurity Certificate Program, specifically Module 1 of Connect and Protect Networks and Network Security.
Good stuff.
And we've also pulled in some related materials on cloud computing and, those crucial TCP/IP and OSI models.
Absolutely essential models.
Our goal today, it's to give you a sharp, engaging grasp of how networks are built, how your data actually travels across them,
Right.
and those initial layers of security.
And keeping it clear. Hopefully.
Yeah, trying to keep it clear, less jargon.
Precisely. And understanding that underlying structure, it isn't just academic, is it? It's really the bedrock of understanding security itself.
Right.
I mean, without knowing the network's anatomy, trying to spot vulnerabilities or, potential attack vectors becomes incredibly difficult.
Yeah, you're kind of flying blind. Totally. So we're going to dissect the essential components. We'll start with the tangible things, the network devices.
The hardware?
The hardware, yeah. And then move on to the more abstract, but equally vital logical frameworks that sort of govern communication.
Exactly. So picture this as your personal learning journey today. We'll kick off by looking at the individual pieces, the things that make up a network, computers, routers, all that gear. Then we'll see how these pieces are actually organized, the network's architecture.
How they connect.
Right. And we'll definitely touch on modern cloud-based networks because they've really reshaped the landscape.
Oh, absolutely.
And finally, we'll dig into those foundational models, TCP/IP and OSI. They're kind of like the instruction manuals for device communication.
Good analogy.
Okay, so let's get started. First up.
The physical building blocks, network devices.
Right. So at their heart, these devices, they exist to maintain information and deliver services. They're the workhorses, really, of our digital world. And these devices, they range from, your personal laptop to really sophisticated enterprise servers. They connect either through physical cables, like Ethernet, or, wirelessly via Wi-Fi.
Okay.
And once they're connected, they talk using data packets. Think of them as small digital containers carrying vital details, where the data came from, where it's going.
Right. And, you probably interact with loads of these devices every single day.
Oh, for sure.
Think about your personal computer, your laptop, smartphone, tablet. A key thing to remember here is that each one has a unique identifier on the network.
That's important.
Yeah, an MC address that's like its hardware fingerprint, right?
Yep, fixed to the hardware.
And an IP address, which is more like its current location or address on the network, can change.
Dynamic, often, yeah.
Plus, they all need a network interface. That's the physical part, or sometimes virtual part, that lets them actually send and receive those data packets.
Got it. Then we have firewalls. Now, picture a firewall, maybe like a security checkpoint, controlling who gets in and out of your network.
Okay, like a gatekeeper.
Exactly.
Yeah.
Often the very first line of defense. It continuously monitors all the traffic coming in and going out.
All of it.
Well, all the traffic between your internal network, could be your home network, could be a big corporate one, and the outside world, like the internet.
Okay.
And it uses a set of predefined security rules to decide, what's allowed through and what gets blocked.
Right.
But it's really crucial to remember, and the materials stress this, a firewall is just one piece. It's one component in a much broader layered security strategy.
Good point. Not the whole solution.
Definitely not.
Okay, good analogy with the checkpoint.
Yeah.
Now, let's talk about servers. These are the providers, right? They offer up information and services to other devices, which we call
Client-server model.
Exactly. That interaction follows the client-server model. So, for instance, when you type a website address into your browser, your computer, the client sends a request, maybe to a DNS server, to find that website's actual IP address.
Translates the name to a number.
Right. And once it has that number, your computer can then ask for the website files from, probably another server, the web server.
Yeah.
And it's similar for other things like file servers storing files or mail servers handling your email. It's this whole ecosystem of requests and responses.
It is. And within a local network, inside your house or office, we have devices that manage how that traffic flows locally. Hubs are kind of the older technology.
Right. You don't see them much anymore.
Not so much. They act as a central connection point, but they lack sophistication. When a hub gets data, it basically just shouts it out to every single device connected to it.
Not very private.
Not at all. As you can imagine, that creates a pretty big security hole. It makes eavesdropping really easy. So modern networks have pretty much moved on to using switches instead.
Absolutely. Switches are way smarter. They actually learn which devices, identified by their unique MAC addresses, are connected to their specific ports.
They build a little table.
Yeah, exactly. They keep this info in what's called an AMAC address table. So instead of just broadcasting everywhere like a hub, a switch forwards a data packet directly to the device it's intended for based on that MAC address.
Much more efficient.
Way more efficient and more secure, too, within that local network. This operates at the data link layer of the TCP/IP model. Understanding that MAC address mapping is really key for local network security.
Definitely. Now, what happens when you need to connect different networks together? Say your home network to the internet, or maybe a company's main office network to a remote branch.
Ah, that's router territory.
That's where routers come in, exactly. Routers operate at a higher level, the network layer of the TCP/IP model, and they use IP addresses to direct traffic.
So AMAC addresses for local, IP addresses for between networks.
That's a good way to think about it, yeah.
Yeah.
The router looks at the destination IP address in the packet's header and figures out the best path to get it there. This often means hopping across multiple routers on the way.
Like a relay race.
Kind of, yeah. And just like we mentioned with firewalls, some routers actually have firewall features built in too to filter traffic. How these routing tables are managed is, well, it's a key part of network efficiency and security.
Right. And for most of us at home or in a small office, getting that initial internet connection usually involves a modem.
The box from your ISP.
Yeah, that one. It talks to your internet service provider, maybe over phone lines or more commonly now, coaxial cable lines. It basically translates the internet signals into something your router can understand and vice versa.
Okay.
But, for big organizations pushing lots of data, they often use other faster broadband technologies, not just the standard modem.
Makes sense. High volume needs different solutions. And finally, for those of us who like cutting the cord, we have wireless access points, or WNAs.
Wi-Fi,
exactly. These devices use Wi-Fi standards and radio waves to create wireless networks. They let your laptops, smartphones, tablets connect without plugging in cables.
Super convenient.
It is. These wireless signals then connect back to your router, usually, and from there out to the wider network or the internet. So really, whether it's a wired connection or wireless, all these devices are constantly swapping those data packets, each tagged with where it came from and where it needs to go.
Okay, so we've got a handle on the individual bits and pieces. Now, how do we actually, visualize how they're all connected? That's where network diagrams come in, right?
That's exactly right.
Yeah.
Think of network diagrams as like the visual blueprint for a network's infrastructure.
Maps.
Yeah, basically maps. They show all the different network devices and, crucially, how they're connected to each other. Security analysts rely really heavily on these.
Why is that?
Well, they give a clear visual picture of the network structure. And that's absolutely essential if you're trying to spot potential security weaknesses or figure out the best way to place security controls. You need to see the layout.
Makes sense. You need the map to plan the defenses.
Yeah.
And these diagrams, they use simple icons, right? Like maybe a rectangle for a computer, a different symbol for a router.
Yep. Standard symbols usually.
And then lines, maybe dotted lines, showing the connections between them. The materials we looked at even had an example diagram. It showed a modem connected to the internet.
Okay.
Then a firewall right after it.
Good practice.
Yeah. Then a router directing traffic to various devices, some wireless, computers, laptops, printer, even a server.
Well, typical small network setup.
Pretty much. And it also mentioned that in more complex setups, you might see a switch connecting, say, two routers together for load balancing.
Yeah, to spread the traffic load.
Yeah.
Makes the network faster, more resilient if one pad has issues.
Exactly. Seeing it all laid out visually like that, it really helps you understand how data flows and where potential bottlenecks or, vulnerabilities might be hiding.
Absolutely. It makes the abstract much more concrete. So building on that, how networks are physically put together and mapped out, let's shift gears a bit and explore how cloud computing has really changed this whole picture.
Ah, the cloud. Yeah, big topic.
Huge. We've moved, in many cases, beyond that traditional model where all your network gear, servers, everything is physically located in your office, building what we call on-premise networks.
Right. Cloud computing, it's fundamentally about using remote servers, applications, services that are hosted out on the internet, usually by these big companies called cloud service providers or CSPs.
Like AWS, Google Cloud, Azure.
Exactly. So instead of buying and managing all that hardware yourself, you essentially rent it or lease it from a CSP.
And these providers, they operate these enormous data centers just packed with servers, often located all over the world.
Global infrastructure.
Totally. And you, as a customer, whether you're an individual or a big company, you access and manage these services using things called APIs, application programming interfaces, or often through web-based dashboards, management consoles.
Okay. And the readings break down these cloud services into like 3 main types, right?
Yeah, 3 main categories. First, there's SaaS, software as a service.
SaaS like Gmail or Microsoft 365.
Exactly like that. Think of it as ready-to-use software applications you just access over the internet. No installation, no managing updates on your end, mostly.
Convenient.
Very. A key security thought here, though, is making sure that CSP has really solid security measures protecting the application and, more importantly, your data within it.
Right. Trusting the provider. Okay, what's next?
Next is IaaS, infrastructure as a service.
Infrastructure.
Yeah.
So like the building blocks.
Precisely. This gives you the fundamental computing bits in the cloud, virtual servers, virtual storage, networking resources. It's like getting the raw materials to build your own IT setup, but without buying any physical hardware.
So you can move your existing applications there.
That's a very common use case, yeah. Companies use IaaS to migrate and run their existing apps in the cloud. But a big security point with IaaS is you are largely responsible for configuring and managing the security of those virtual components.
Ah, okay. More control, but more responsibility.
You got it.
Mm-hmm.
And the third main type is PaaS, platform as a service.
Platform for developers.
Exactly. This is tailored for developers. It gives them the tools, the frameworks, the services they need to build, test, and deploy their own custom cloud-based applications without worrying about the underlying infrastructure.
So they can just focus on coding.
Pretty much. Now, a crucial security aspect for PaaS is making sure the applications being developed are secure and handle data properly. Plus, you need to understand the security controls the PaaS provider themselves offer.
Okay, SaaS, IaaS, PaaS. Got it. Now, it's not always just one or the other, is it? People mix and match.
Oh, definitely. It's rarely all or nothing. We see a lot of hybrid cloud setups.
Hybrid, so part cloud, part on-premise.
Exactly. Organizations strategically blend their own internal on-premise infrastructure with cloud services from a CSP. Maybe keep sensitive data in-house, but use the cloud for web servers or development.
Makes sense. Best of both worlds, maybe?
Potentially. And some even go multi-cloud.
Multi-cloud, using more than one CSP.
Yeah, leveraging services from, say, AWS and Azure and Google Cloud, maybe picking the best service for a specific job from each. The reading actually mentioned that hybrid cloud is probably the most common model right now.
Why is that?
Often it's about optimizing costs, but also keeping more direct control over certain critical or sensitive systems or data.
Okay. And building on this idea of virtual resources, there's also SDNs, right? Software-defined networks.
Yes, SDNs. In the cloud world, SDNs basically mean virtual versions of traditional network gear, things like virtual switches, virtual routers, virtual firewalls, often hosted in those CSP data centers.
So networking becomes software.
In essence, yeah. Though it's worth noting that even modern physical network devices are increasingly able to run virtualized functions too. A really big benefit of SDNs, especially in the cloud, is the centralized control it gives you over network policies and security rules.
Ah, easier management potentially. So what are the big drivers? Why are cloud and SDNs so popular?
Well, the readings highlighted 3 main advantages. First, reliability. Cloud services generally offer high availability, meaning they're up and running most of the time. Plus secure connections and, pretty consistent operation. Less downtime, hopefully.
Good. What else?
Second is cost, or rather, potential cost savings.
Ah, the money aspect.
Always important. Because CSPs operate at such a massive scale, they can often provide these virtual resources much cheaper than an organization could by buying, maintaining, and constantly upgrading its own physical stuff.
Economies of scale.
Exactly. Economies of scale. Now, the flip side is you need to manage that cloud spending carefully, avoid unexpected bills, and maybe watch out for vendor lock-in.
Right, getting stuck with one provider. Okay, so reliability, cost. What's the third?
Scalability. This is a huge one.
Being able to grow or shrink easily.
Precisely. If your company suddenly needs way more computing power or network capacity, maybe for a big sale or event,
Yeah.
you can typically scale up almost instantly using the CSP's APIs or web console. It's elastic.
Pay for what you use.
Exactly. It's an elastic consumption model. You pay for the resources you use when you need them. The reading gave a good example. If you're suddenly facing a cyber threat, you can quickly spin up and configure extra defenses, like web application firewalls, LoveUFs, or intrusion detection systems, IDSEPS, in the cloud.
That's powerful. Quick response.
Very. But again, a security challenge there is making sure your security policies and your visibility keep up as things scale up and down so quickly.
Right. Consistency across a changing landscape.
Exactly. So we've seen how devices are organized, how the cloud offers these new ways to build networks. Now let's dive into the fundamental models that really govern how these devices actually talk to each other, starting with the TCP/IP model.
Okay, TCP/IP, yeah. You hear this one mentioned all the time. It's like the foundational framework for understanding how data gets structured and sent across a network, right?
That's exactly it. It's a really essential way for anyone working with networks, especially in security, to visualize these, well, pretty intricate processes.
It breaks it down into layers, doesn't it?
Yeah, it does. The TCP/IP model organizes the whole communication thing into 4 distinct layers. Down at the bottom, closest to the actual hardware, is the network access layer.
Network access is sometimes called the data link layer, too.
Yeah, you'll hear both terms. This layer, it's all about the physical transmission of data packets across a specific network segment. Think network cables, Wi-Fi cards, hubs, modems. They all operate down here.
Okay, the physical connection.
Right. And also crucial at this layer is something called ARP, the Address Resolution Protocol.
ARP, what's that for?
It's basically the translator between IP addresses and those physical ME addresses we talked about earlier. It lets devices find the specific hardware address of another device on the same local network when they only know its IP address.
Needed for local delivery. Okay, layer 1 network access. What's above that?
Moving up, we hit the internet layer, also often called the network layer.
Okay.
The main job here is making sure a data packet reaches the correct destination host, even if that host is on a totally different network, maybe across the world.
This is where IP addresses really matter then.
Absolutely. This is where the source and destination IP addresses get attached to the packets. The internet layer also figures out the protocol needed for delivery. The 2 key protocols here are IP itself, the internet protocol.
The main one?
The main one, yeah, handles the addressing and routing, and also ICMP, the Internet Control Message Protocol.
ICMP sounds like error messages.
That's a big part of it. What's interesting is IP itself is mostly concerned with just getting the packet to the right network, the right general area. It actually relies on the next layer up, the transport layer, specifically TCP or UDP, to handle the reliable or maybe just efficient delivery to the specific application running on that destination machine.
Okay. IP gets it to the door, something else gets it to the right room.
Good way to put it. And ICMP, yeah, it acts like the network's feedback system. It sends messages about problems like if packets got dropped, if there are connectivity issues, or maybe if a packet needs to take a different route, think ping.
Ping uses ICMP. Okay, so internet layer handles routing between networks using IP. What's next?
Ascending further, we reach the transport layer. This layer's job is all about delivering data between 2 specific systems or applications and managing the flow of that traffic. The 2 big players here are TCP and UDP.
TCP and UDP. Heard of those? What's the difference again?
Okay, so TCP Transmission Control Protocol is connection-oriented.
Connection-oriented, like a phone call.
Exactly like making a phone call. First, you establish a connection, the handshake. Then you have reliable 2-way communication where delivery is basically guaranteed. Then you hang up, terminate the connection.
Okay, so TCP makes sure the data gets there?
Yes. It ensures data is reliably sent to the right destination service. It uses something called port numbers in its header to identify which specific application or service the data is for, like an apartment number on a building address.
Got it.
And if any data gets lost or arrives corrupted during the trip, TCP will notice and automatically ask for it to be resent. Reliable.
Okay, reliable but maybe slower. What's UDP then?
UDP is the user datagram protocol, and it's connectionless.
Connectionless, like sending a postcard.
Perfect analogy.
Yeah.
You just write the address and drop it in the mail. No prior connection set up. No guarantee it'll arrive. Or even that multiple postcards will arrive in the order you sent them.
Sounds risky. Why use it?
Speed. Because it skips all the connection setup and acknowledgement stuff, UDP is much, much faster. It's often used for things where speed is critical, even if you occasionally lose a tiny bit of data. Think video streaming, online gaming, DNS lookups sometimes.
Ah, okay. Losing one frame in a video isn't the end of the world, but lag is terrible.
Exactly. Performance over perfect reliability in those cases.
Makes sense. Okay, transport layer. TCP for reliability, UDP for speed. What's the top layer?
Finally, at the very top of the TCP/IP stack, we have the application layer. This is the layer that you, as a user, interact with most directly through software.
So my web browser, my email client.
Precisely. This layer defines the actual network requests and responses your applications make. It determines which internet services and apps you can access.
And this is where all those familiar acronyms live, like HTTP for web stuff.
Yep. HTTP for web browsing, HTTPS for secure web browsing, SMTP for sending email, SSH for secure logins, FTP for file transfers, DNS for translating names to IPs. All those application layer protocols operate here.
But they all rely on the lower layers, right? Like TCP or UDP and IP.
Absolutely. They define what needs to be sent, but they depend entirely on the transport, internet, and network access layers below them to actually handle the addressing, routing, and physical transmission of the data across the network.
Okay, that paints a pretty clear picture of the TCP/IP model. Network access, internet, transport, application.
Got it. Now, alongside TCP/IP, there's another important conceptual model you often hear about, the OSI model, Open Systems Interconnection.
Right, the OSI model. The reading mentioned this too. It's another way to think about network communication, but it has more layers.
It does. While TCP/IP, as we saw, has 4 layers, the OSI model expands this framework out to 7 layers.
7 layers. Why the extra detail?
Well, network professionals often find the OSI model useful when they're talking about specific network problems or maybe security threats. Because it breaks down the process into more granular steps, it can sometimes make it easier to pinpoint where an issue might be occurring.
So like more specific troubleshooting.
Kind of, yeah.
Yeah.
You can say the problem seems to be at layer 3, or we need a layer 7 firewall. The reading suggested thinking of TCP/IP as more practical, reflecting how the internet actually works day to day. While the OSI model is perhaps a more comprehensive theoretical reference standard for all types of network communication, not just internet protocols.
So TCP/IP is like the simplified working version, and OSI is the detailed textbook version.
That's a pretty good way to look at it, yeah.
Yeah.
TCP/IP is streamlined for the internet. OSI aims to be a universal reference. But honestly, understanding both gives you a really well-rounded perspective on how networks function.
Okay, so let's quickly walk through those 7 OSI layers then. Where do we start? Top or bottom?
Let's work our way down, starting from the top. Layer 7, which is the application layer.
Okay, application layer. Same as in TCP/IP, right? Where the user interacts.
Exactly the same concept. This is where your software applications, live web browsers using HTTP to HTTPS, email clients using SMTP, DNS lookups happen here, direct user interaction with network services.
Got it. Layer 7. What's layer 6?
Layer 6 is the presentation layer. This one doesn't have a direct equivalent in the standard 4-layer TCP/IP model.
Okay, what does it do?
It's all about data format and translation. It makes sure that data sent from the application layer of one system can actually be understood by the application layer of another system.
Oh.
It handles things like character encoding conversion, so text displays correctly, data compression to make transmissions faster, and importantly, encryption and decryption like SSL/TLS used for HTTPS. It presents the data in a usable format.
Ah, okay. Formatting, compression, encryption. Presentation layer, layer 6. Next.
Layer 5 is the session layer, another one not explicitly in the common TCP/IP breakdown.
Session layer sounds like managing connections.
You got it. This layer is responsible for establishing, managing, and then tearing down connections or sessions between two applications.
Like the TCP connection setup, but maybe more general?
Sort of. It handles things like authentication, making sure the parties are who they say they are before starting a session. It can also manage dialogue control, who talks when, and synchronization, like putting checkpoints in large file transfers, so if it breaks, you can resume from the last checkpoint instead of starting all over.
Useful. Okay, layer 5 session layer. Down to layer 4.
Layer 4 is the transport layer. Now this one does map directly to the TCP/IP transport layer.
Ah, okay, so this is TCP and UDP again.
Exactly. Responsible for reliable end-to-end data delivery between hosts. It handles segmenting data from the upper layers into smaller pieces for transmission and reassembling them correctly at the other end. It also manages flow control, so a fast sender doesn't overwhelm a slow receiver, and error checking. TCP and UDP leave here.
Okay, transport layer, layer 4. Same functions as in TCP/IP. Layer 3.
Layer 3 is the network layer. Again, this maps directly to the internet layer in TCP/IP.
So IP addresses and routing.
Precisely. Its main job is logical addressing, IP addresses, and figuring out the best path to route packets across potentially multiple interconnected networks from the source to the final destination. Routers operate primarily at this layer.
Got it. Network layer, layer 3. What's layer 2?
Layer 2 is the data link layer. This corresponds roughly to the network access layer in TCP/IP, but OSI sometimes splits hairs a bit more here.
Okay, data link. So local network stuff, AANAC addresses.
Exactly. This layer deals with organizing data transfer within a single network segment between directly connected devices. It uses physical addresses, MAC addresses. Switches operate mainly at this layer. It also handles framing the data correctly for the physical medium and do some error detection for that specific link.
Okay, switches, MAC addresses, local delivery, layer 2, data link. That leaves layer 1.
Layer 1, the physical layer, the absolute bottom. As the name suggests, this is all about the physical hardware.
Cables, connectors, hubs.
Yep. Cables, like Ethernet or fiber optic. Connectors, hubs, modems, repeaters, network interface cards, the physical part of them. It defines the electrical, optical, or radio signals used to actually transmit the raw bits, the zeros and ones, across the physical network medium. How voltage represents a 1 or a 0, for instance.
So turning the digital data into actual physical signals.
Exactly. So application 7, presentation 6, session 5, transport 4, network 3, data link 2, physical 1. While TCP/IP is maybe more practical day to day, the OSI model gives that really detailed, layered view of the whole communication process, like peeling an onion layer by layer.
Okay, that helps clarify the OSI model. 7 layers, more theoretical detail. Now let's zoom back in on the network layer, which is layer 3 in OSI, or the internet layer in TCP/IP. You said this is where the crucial stuff happens for getting packets across different networks.
Absolutely. The network layer is really fundamental for internet communication. Its whole purpose is getting data packets from a source device all the way to a destination device, even if they're on completely separate networks, potentially thousands of miles apart.
And that involves routing.
Yes, routing is key. Routers at this layer make decisions. They look at the destination IP address in a packet's header and consult their internal routing tables to figure out the best next hop, the next router to send the packet to get it closer to its final destination. This happens step by step, router to router.
Okay. And these data packets, you call them IP packets for TCP and datagrams for UDP.
Yeah.
They all contain header information.
They do. That header is critical. It contains essential control information, including, most importantly, the source IP address, where it came from, and the destination IP address where it's going.
What else is in there?
Well, it also usually includes the overall size of the packet and, very importantly, an indicator telling the receiving system what kind of data is inside specifically, which transport layer protocol, like TCP or UDP, should handle the payload.
Okay. The reading went into quite a bit of detail on the IPv4 packet format, didn't it?
It did. It's worth understanding. An IPv4 packet has 2 main parts, the header and the data payload.
Header first. How big is that?
The IPv4 header is typically 20 bytes long, but it can be up to 60 bytes if optional fields are used. Those first 20 bytes contain the really core information needed for routing.
Like the addresses.
Yep, source and destination IP addresses are in there, along with other fields. The rest of the packet, after the header, is the actual data payload, the message or information being sent. And that payload can be up to 65,535 bytes in theory, though often smaller in practice due to network limits.
Okay, 20 bytes for the standard header, and the reading broke down like 13 fields within that header. Seemed like a lot.
It does seem like a lot, but each field has a specific purpose. Let's quickly touch on them. First, there's the version field. Simple enough. It just says this is an IPv4 packet, values 4.
Okay.
Then IHL, or header length, tells the receiving device how long the header actually is in 32-bit words, so it knows where the data part begins. Usually 5, meaning 5 for 20 bytes.
Got it.
Type of service, TOS, now often called Differentiated Services Code Point, DSCP. This allows routers to prioritize certain types of traffic, like maybe voice calls over email.
Quality of service.
Exactly. Then total length. This is the length of the entire packet header plus data in bytes.
Okay.
Next 3 are related. Identification, flags, and fragmentation offset. These are used if a packet is too big to cross a certain part of the network.
If it needs to be broken up.
Right. If it has to be fragmented into smaller pieces, these fields allow the receiving end to put all the pieces back together in the correct order to reconstruct the original packet.
Clever. What's next?
Time to live, or TTL. It's a really important one. It's not actually a time, it's a counter.
A counter. What is a counter?
Hops, basically. Every time the packet passes through a router, the router decreases the TTL value by at least 1. If the TTL hits 0 before the packet reaches its destination,
It gets dropped.
it gets discarded, yes. And usually the router sends an ICMP time-exceeded message back to the original sender.
Why do that?
It prevents packets from getting stuck in routing loops and endlessly circling the internet forever if something goes wrong with the routing tables. It's a safety mechanism and useful for diagnosing problems with tools like traceroute.
Ah, okay. TTL prevents infinite loops. Makes sense. Keep going.
Okay, then protocol. This field tells the receiving system which protocol is inside the data payload.
Yeah.
Is it TCP, value 6? Is it UDP, value 17? Is it ICMP, value 1? Very important for demultiplexing.
Tells it who to hand the data off to upstairs.
Exactly. Then header checksum. This is an error checking value calculated just for the header. Routers recalculate it. If the checksum doesn't match, it means the header got corrupted somehow during transit, and the packet is usually just dropped. Doesn't check the data, just the header.
Okay, basic integrity check for the routing info.
Right. Then the big ones. Source IP address, 32 bits, the sender's address, and destination IP address, 32 bits, the recipient's address. Fundamental for routing.
The to and from addresses.
Precisely. And finally, the options field. This isn't always present, but it allows for extra control information, sometimes used for things like recording the route taken or specific security features, though it can slow down processing.
Wow. Okay, that's a lot packed into 20 bytes. Version, IHO, TDOS, total length, ID, flags, offset, TTL, protocol, checksum, source IP, destination IP, options.
Got it. It's dense, but crucial for making the internet work.
Yeah.
We've been talking IPv4, but we're running out of IPv4 addresses, right?
Yeah, I've heard that. That's where IPv6 comes in.
Exactly. IPv4 uses 32-bit addresses. That gives us about 4.3 billion unique addresses.
Sounds like a lot.
It did back in the 70s. But with, smartphones, laptops, servers, smartwatches, smart fridges, everything connecting, we actually started running out. IPv4 address exhaustion is a real problem.
So IPv6 was developed to fix that? How does it do it?
Well, the biggest change is the address size. IPv6 uses 128-bit addresses.
128 bits. How many addresses is that?
It's astronomical. Something like 340 undecillion addresses. That's 340 followed by 36 zeros. Basically, more addresses than we could ever conceivably need. Enough to give every grain of sand on Earth multiple addresses.
Okay, so address exhaustion solved. How do they look different? IPv4 is 4 numbers with dots.
Right, like 198.51.100.0.0. IPv6 addresses are usually written as 8 groups of 4 hexadecimal digits separated by colons.
Hexadecimal. Uh-oh.
Yeah, using numbers 0, dan 9, and letters AF. So an example might be something like 2001.00000.83.0370.7334.
Looks complicated.
It can seem that way.
Okay.
But they're shorthands. For instance, leading zeros in a group can be omitted. And if you have consecutive groups of all zeros, you could represent them with a double colon, but only once in an address.
Okay, so Wolf means a bunch of zeros here.
Pretty much. Now, besides the address length, IPv6 also changed the packet header format.
How so? Simplified it.
Yes, actually. The IPv6 header is designed to be simpler and more efficient for routers to process. For example, it got rid of the IHL field, the identification and flags fields related to fragmentation. Fragmentation is handled differently.
Okay, anything new added?
It introduced a flow label field. This can be used to mark packets belonging to a specific flow that might require special handling by routers, like specific quality of service. And importantly, IPv6 was designed with security features like IPsec more integrated from the start, though they're often optional.
Okay. And the reading mentions some security benefits of IPv6 too.
Yeah, a couple points. The more efficient routing in IPv6 can potentially improve network performance slightly. And maybe more significantly, because there are so many addresses, it eliminates the need for network address translation and NOT, which is heavily used in IPv4 to conserve addresses, but can sometimes complicate things. It also gets rid of the possibility of private IPv4 address collisions within large organizations.
Interesting. So more addresses, simpler header in some ways, built-in security considerations.
That's the gist. And what's really key from a security perspective, whether you're looking at IPv4 or IPv6, is that analyzing these fields in the IP packet header gives you crucial information.
Like what?
You can see where traffic is coming from, where it's going, what type of communication it is based on the protocol field. Understanding these details is absolutely fundamental if you're, say, analyzing network logs, investigating an incident, or configuring firewall rules. You need to understand the language of IP packets.
Right. It tells the story of the network traffic. Okay, so to kind of wrap up our deep dive today, We covered a lot of ground.
We really did.
We started with the basic building blocks network devices like computers, firewalls, servers, routers, switches, WAPs, understanding what each one does.
Their individual roles.
Then we looked at network diagrams, how we visualize this structure.
The blueprints.
Then we jumped into the modern world of cloud computing and software-defined networks, talking SaaS, IaaS, PaaS, hybrid clouds, and the benefits like reliability, cost, and especially that scalability.
And some of the challenges, too.
Yeah, good point. And finally, we really dug into the models that explain communication, the 4 layers of TCP/IP and the 7 layers of OSI.
Comparing them.
Right. And we finished with a close look at the network layer, focusing on the IPv4 packet header fields and the big shift towards IPv6 with its massive address space and header changes.
And that foundational knowledge, it's just, well, it's absolutely critical, isn't it?
Seems like it.
It gives you that essential grasp of how the digital world is actually put together underneath, and those first, the vital steps towards understanding network security. As you go deeper into more complex cybersecurity topics, having this solid base, this understanding of the basics, it's going to be your essential building block.
Couldn't agree more. So here's maybe a final thought for you, the listener, to chew on. Considering this explosion of connected devices, everything from smartwatches to huge industrial sensors, how do you think the ongoing accelerating adoption of IPv6 with its almost limitless addresses might change the game for cybersecurity? What new challenges, but also maybe what new opportunities does that create?
Or, another angle, as we rely more and more heavily on cloud services, what totally new security thinking, what new paradigms do organizations need to develop, going beyond just the traditional firewall and server defenses we've always used for on-premise networks?
Definitely some big questions there. Food for thought as you continue exploring this field.